Just remember, your exam is on the 2nd of December, Thursday in lab. Uh, has he given any more information about like how much time you'll have for that? Like, has he said that some of you are going to be doing your presentations? Like, he's going to try and get through most of them on Tuesday, or is he still having some on Thursday?
He said he thinks that we might finish it on Tuesday.
Okay, good, good, because that means that you can get the entire 3 hours to cry over enolates, which will be nice. So, um, that just means I can make it even harder, right? No. Well, maybe. We'll see.
We might have half the class might have to take it on Thursdays.
So we'll see. So, with that, I'll also put up some more. So if you notice, in extra resources just above that enolates guide, if you take a look at Mrs. O's website, the password is Dendrimer, all caps. There's a bunch of SIs on the bottom for all these enolate reactions. It would be a good idea to take a look at those. So there's 5 different types of enolates, right? We have aldol, the claisen. Within the claisen, we have the malonic ester and the acetic ester variants. We have the Michael additions, and then the Stork enamine synthesis, and then condensation for aldol and claisen and all that. So those are there. Definitely use those as study materials. I can try and find some of her exams as well. I think I want to say exam 4 last time had some enolate stuff, so that one's just above that as well. Okay, so that was all of that stuff. Let's talk about carbohydrates. And like I said, the chemistry here is not that difficult, which is nice. And we're going to see that you'll be studying these a lot more in biology. If you've taken biology already, I'm sure you've already had to deal with like memorizing carbohydrates and amino acids and all that fun stuff, because apparently that's a useful skill. I disagree with that, but that'll help you out. So we're going to see with covering carbohydrates, there's just a few things that we're going to cover that are probably not covered in biology class, but we'll do a little bit of the basics as well. So carbohydrates are they generally follow the formula of CxH2OX for monosaccharides. Commonly, we'll see that we have the variation of these hexoses, as we'll call them, like glucose, like fructose. The more common sugars we have are these 6 carbon ones, and as you can see here, they follow that idea of having 6 carbons and then 6 waters attached onto them. And of course, that doesn't mean like water molecules are actually like just directed to the carbons. We're going to see that there's a variety of ways these can be drawn. And so I'm going to be flipping you off a few times in class today. That is not in oversight. Just be aware it's the easiest way to remember glucose's structure. So just be aware of that as we're going through. So if we take a look at glucose, which is our most common monosaccharide, our simple sugars, we're going to see that monosaccharides like glucose have an aldehyde, and then the rest are going to be alcohols. And we usually talk about these sugars in Fischer projection. That's not O2, that should be OH. And the way to remember glucose's structure is to flip off your page. If you take your hand, and I guess I'm doing this in mirror image, so I'll use my left hand, but this should be your right hand. I think it's mirror image. I don't know. Let's see what we're looking at here. So we need it right, left, right. So that's left, right, left for you guys, which is not what we want. Okay, so it is indeed still our right hand. So we're going to see that glucose, if you flip off your your page, you'll see that's the structure of glucose. So this hydroxy points to the right, to the left, to the right, to the right. And that's the structure of glucose. Easiest way to remember it. This is D-glucose, which has that formula C6H12O6. We can classify glucose further, or more generally, rather, as an aldohexose. It falls under that category. We're going to see that this means there's an aldehyde. In your sugars, you're either going to have an aldehyde or a ketone, and we'll see those as well. Hex, of course, refers to 6 carbons, and then the ose part refers to sugar. So carbohydrates or sugars would end with ose. And so we're going to see that there are 8 different aldohexoses, which are all various diastereomers, and then we have all of their enantiomers as well. We're going to see that 2 more common ones that we'll want to probably learn. Of course, I can't make you memorize these. I don't think it's very useful to do that. If you know the structure of glucose, you can get all of the other structures by understanding how glucose and your other sugars are related to each other. We've got 2 more that I want to put up. So Mannose has the following arrangement of hydroxys. Notice the aldehyde and the bottom CH2OH are the same, and it's going to be the same for all of these aldohexoses. And then Galactose has this following one. I'll write their names out as well. This is D-glucose. This is D-mannose. And this is D-galactose. We'll talk about these in a little bit. I have fun hand signals. You can remember these as well. Mannose is like what we do, if you want to pretend you have a gun as a child, you do the little, Mannose has that arrangement. So left, left, right, right, pointing with those hydroxy groups. So again, glucose, flip off the page, right, left, right, right. Galactose is your little spaceship. Wow, I can't really do this. How did I do this? Like this, maybe? I guess so. Where's Galactose? Yeah. I don't know. Ooh, spaceship. Ooh. And so you have, I guess, pointing the other direction. You have the 2 there, and then 2 pointing to the right. So basically, though, if you know glucose, you can get all other aldohexoses by looking at how they're related. We're going to see that numbering these sugars always starts at the aldehyde, because that's our highest priority, right? We're going to see that the relationship between mannose and glucose, we see the only thing is that carbon 2 has switched sides. We have everything else on glucose is the same, except carbon 2 is it's a diastereomer at carbon 2. And we call that an epimer. So mannose is a C2 epimer of glucose. It varies its chirality at carbon 2. So we've switched the position of carbon 2. So again, if you flip off your paper, you'll know glucose. And then you have to think, okay, here's carbon 1, my aldehyde. Carbon 2 is here. Poof, now I've got mannose. And so if you can remember what these epimers are, then it's very easy for you to come up with the structure. And I can, it's pretty easy that way. And of course, galactose is a C4 epimer. And usually we refer to these comparing to glucose. Wow. Glucose. And let's just define epimer. An epimer is a diastereomer at a specific carbon. So when we're talking about epimers, we're looking at generally our reference structure, which is glucose, the most common one. And we're going to be looking at diastereomers at various carbons. So mannose is a diastereomer of glucose at carbon 2. Everything else in mannose is identical to glucose. For galactose, everything is identical except carbon 4, which has been swapped in terms of its stereocenter. So that's a C4 epimer of glucose. And if you are really interested, you can see in the extra resources tab, I have all of our aldohexoses in there. So you have allose, maltose, glucose, mannose, gulose, idose, galactose, and talose. There's no need to memorize these structures, although, again, it is pretty helpful if you memorize glucose. That'll make things a little faster for you. We'll see there's other patterns, like allose, for example, has all the hydroxys pointing to the right. Just random little mnemonics there. Again, you don't need to memorize these. Not only because it's online, but I wouldn't make you memorize them anyway because that's pointless. So, except maybe glucose. That's kind of our aldohexoses. If we look at some ketoses, the ketoses will have one fewer stereogenic center, so we're only going to have 4. If we take a look at the ketohexoses, most common one is fructose. All right, let's take a look here. So, ketohexoses, we're going to see that for fructose, it's going to be the same kind of basic structure, except we're going to have a ketone in here. And in the Fischer, we usually draw it like that. In this case, we have 2 non-chiral carbons, achiral carbons, the top and the bottom. And then for fructose, it's everything else is the same on glucose. So flip off your paper again, but now this is our ketone here. So we have our left-pointing one and our 2 right-pointing ones. And so this is fructose. It is essentially the same as glucose, except now we have a ketone at carbon 2. Of course, we're going to number these closer to our higher priority group, right? So we do see ketohexoses in nature as well. So we do have these pretty commonly. Fructose is pretty common. There are 3 other ketoses on carbon 2. Of course, if you put it to carbon 3 or carbon 4, well, I guess the carbon 4 would be the same as carbon 3. Because then you just have an inversion. But we usually are looking at C2 ketohexoses here. So those exist as well. All right, we're going to see that when we're looking at these sugars, we're going to see that oftentimes we kind of draw them as Fischer projections, but in reality they don't tend to adopt these conformations. So Fischer projections are very useful for the stereochemistry, but we're going to see that like 0.01% of sugars exist in what's called this straight chain form. That would resemble the Fischer projection. We're going to see that by and large, all these will adopt cyclic conformations. And we'll take a look at how that's going to manifest itself. I do want to point out one thing, though. We've seen that all of these hexoses, I mean, you can have pentoses, tetroses, trioses as well. There's just more. They all behave the same way. With these, we see that they all start with D. And that may not be something we're familiar with. D stands for dextrorotatory. So these rotate polarized light to the right. They're chiral, right? Chiral compounds rotate light. These all rotate things to the right. But it turns out that we don't really talk about this anymore in terms of that. It's better to say that the D for us for a hexose means that your fifth carbon is the R stereocenter. That's the better way to do it. And if you look, notice in all of these structures, we have our carbon number 5 with its hydroxy pointing to the right. These all have an R stereocenter on carbon 5. And so they're all called D sugars. And these are the ones that are common in nature. We only really ever deal with D sugars. And so the opposite of this would be L sugars, which would be levorotatory. But this is also, in fact, not... I mean, all the D sugars are dextrorotatory. That is true. They rotate things to the right. But we would expect their enantiomers to also rotate, would rotate to the left instead. And that's just not the case. We see that many L sugars still rotate to the right because there's so many chiral centers in here. And so the better way to do this would be to say that it's an S stereocenter on carbon 5. And these L sugars will always be the enantiomers of D sugars. So if we take a look at glucose, remember glucose, here we are, flip yourself off. Boom, there's our glucose, D-glucose. If we want to draw L-glucose, this is D-glucose. Wow. L-glucose would have everything just switched. It would be the enantiomer. So you can either take the structure of D-glucose and just write all the hydroxys on the opposite sides, or you can use your left hand and flip yourself off there, and it'll get you the right structure. So D right, L left. So this would be L-glucose, where it's got that fifth carbon has an S stereocenter instead. And notice it's the complete enantiomer, the mirror image of D-glucose. All right, so pretty okay, right? So let's take a look at what actually these do look like. We're going to see that often, that's not the right carbon. Oops. Undo. We're going to see that sugars often adopt a cyclic form. That's totally not even an oxygen up there, is it? Let's fix that. If we take a look at this, if that oxygen on carbon 5 attacks the aldehyde, it's going to form a 6-membered ring, where one of those rings is going to be the oxygen that was on carbon 5. And so we're going to see here that if we want to draw glucose in a ring form, convention has us put the oxygen in the top right corner. This is called a Hayworth projection. And it's actually pretty easy to get the Hayworth projection of glucose. So glucose in straight chain form looks like this. In Hayworth projection, it looks like this. So you have down, middle finger up, down, and then this one, carbon 5, is actually now our oxygen in the ring. So we don't have to worry about that one. But we take our right hand here and we will now move it up. So we see that carbon, our aldehyde carbon can go either way. It'll go up or down. So I'm going to draw a squiggly on that one. Where was I flipping you off? Okay, this one's going to go down. The middle finger goes up. Then the fourth one goes down. And then the other one is always up in the back. And so this is the Hayworth projection of glucose. And so it's the cyclic form. It's a cyclic hemiacetal. So notice we have an acetal here at this carbon, at carbon 1. This is a hemiacetal. And that carbon number 1 there, the purple one, used to be our aldehyde. So this was carbon 1. And then we had the oxygen on number 5 go ahead and form the ring. And so we see that as a result, we can see this Hayworth projection of glucose as such. So we kind of draw it in fake 3D, where we have things pointing up and down. But if we wanted to be really good chemists, we would redraw this as a chair conformation, because we did not do enough chair conformations in 105, and so it's decided that we're going to do this again. With chair conformations, we always again put our oxygen in that top right position. So the oxygen is always top right in either your Hayworth or your chair conformation. And so if we want to do this, again, this is going to be a squiggly, because this one could have gone either way. We'll talk about which one is going to be better. If you look, number 2 is pointing down, and we're going to see it's going to be pointed down equatorially. Right, because it's the up position that is axial on that carbon, right? So on carbon 2, we have this pointing down. Pointing down is the equatorial position. On carbon 3, we have it pointing up. Pointing up is the equatorial position. And then on carbon 4, we have it also pointing down, which is equatorial. And then the last one we have pointing up, which is, surprise, surprise, equatorial. So we see that glucose the reason that we see glucose as our most common sugar is because everything is equatorial. It is going to therefore be the most stable of all of our sugars, because we're going to have all of our positions being equatorial. And so we're going to see here that we have options on what to do with that squiggly carbon there. I'm going to cheat and copy this because we're going to use it a lot here. I put an asterisk on this because that aldehyde carbon there could go either direction. And we see that we have different names for this. So this one has everything equatorial, where we have completely alternating up, down, up, down, up, down substituents on our sugar. We're going to see that this one is the beta form of the ring. This is the alpha form. And we're looking at about a 67%, 33%, about a 1-to-2 ratio. And again, like, the like super small percentage would be the chain form, right? The Fischer projection. Again, that's not very common, right? As we can see here, most of it will form this six-membered ring, and just having that equatorial hydroxy is just a little bit better, and so we're going to see that most of the glucose will exist as this beta form. Technically, this one would be called, let me write this out, beta D glucopyranose. Pyranose refers to the ring form, because pyran would be the name of the six-membered ring with the oxygen in it. If you remember tetrahydrofuran, that's a five-membered ring with an oxygen. We're going to see our ketoses will adopt fructofuranose forms instead of pyranose. This refers to the six-membered ring with an oxygen. And of course, D-gluco refers to our original sugar. And then the beta refers to the position of that carbon number 1's hydroxy. If it's pointing up, it's beta, which is equatorial. If it's pointing down, it's alpha, which is axial. You can remember it, alpha axial, AA. And so this is the typical version of glucose we see in this cyclic hemiacetal form. And so we'll see that these are going to be kind of interconverting, particularly if these are in acidic or basic solution. If they're as solids, it's unlikely they're going to do anything. But if they are in solution, in either acid or base, they can interconvert between each other. And so we'll see that this happens. This process, by the way, is called Muta Rotation, which is going between different what are called anomers. Alpha and beta are what are called anomers. We'll talk about that in a second. But going between those two in either acid or base, just even mild acid or base, you don't even need a lot. Just catalytic acid or base, these two will be able to interconvert between each other. And so we see that process is called Muta Rotation. Okay. Go ahead.
Question. What are the percentages again?
What are they?
Yeah. It was for
how
what?
much is in one form at a given time? So most of glucose, 67% of glucose is in this beta-D glucopyranose form. And 33% is in alpha. And then 0.01% is in the linear form. So does that answer that?
Yeah.
Cool.
Thank you.
Yeah. So that's just the rough distribution. So these alpha and beta things are called anomers of each other. And they will differ in stereochemistry, at the anomeric carbon. And the anomeric carbon is the one that used to be the aldehyde. Or the ketone. So your anomeric carbon for all of your aldohexoses is carbon number 1, the one that used to be the aldehyde. For your ketoses, it's wherever your ketone is. Most ketoses are at carbon 2, and so that's the anomeric carbon there. And alpha refers to an anomeric, one that points down, and the beta one points up. If we want to look at how these ketoses might form their ring forms, we'll see that they have options. But we'll see that we can see that. So let's look at ketose cyclization. Let's take a look at fructose. Remember, fructose is glucose except with a ketone. So it'll have our hydroxys according to our flipping off hand. When this thing attacks, pops this open, we're going to end up with a 5-membered ring. Instead of a 6-membered ring, because our ketone is 1 carbon down. And again, we will see that fructose can adopt a 6-membered sugar if the that very bottom hydroxy attacks, but it actually is more common to find the 5-membered ring. And if you want to make that 5-membered ring, we usually draw it with the oxygen at the top in the Hayworth projection. And we are going to see that this will be carbon 1, and then our oxygen would be number 5. We're going to see carbon 1 can go either way. So we can have our CH2OH up top, and then our OH down. This would be the alpha form, because our hydroxy is pointing down. And then, again, we would just move everything up. So we now have hydroxy number 2 pointing up. This is carbon 2. The other one is pointing down. Carbon number 4 has its CH2OH pointing up because its oxygen is the one that's part of the ring. And so these will also cyclize, and they're going to form typically 5-membered rings. So we're going to see with fructose, it forms, again, a 5-membered ring. In this particular one, we're looking at the fructofuranose. The furanose refers to a 5-carbon ring with an oxygen. D-fructo refers to D-fructose, of course. And we're looking at the alpha Epimer of this. And so the name of these types of things can give us information about them. We can see that it's alpha D-fructofuranose, and we're going to see that that'll tell us that it's a 5-membered ring, and that's come from D-fructose. All right, and so again, 5-membered rings, these don't have chair conformations, right? So we typically will just leave it as the Hayworth projection. Alrighty.
Scroll up a little bit.
Okay. To what?
Oh, that's fine.
Okay.
I got it. Thank you.
Yeah, so just never here we can make it vertical. Hooray. Alrighty, any other questions on these sorts of things? Alrighty. We're actually going to do some reactions now, as exciting as these reactions are. If we look at reactions of monosaccharides, we can do a few things with them. And for these, we often will talk about certain reactions in chair conformation of things, and some reactions we're going to look in the linear form. So, here we go. Reaction number 1. We have our Pyranose ring here. If we treat this with acetic anhydride or the acid chloride, we can turn all of these into acetyl groups. It's very exciting. So we replace all of our H's with acetyl groups. Awesome. Why you would do this, I do not know, but you can. Remember, in an acetyl group, if I were to really draw them out, acetyl groups are just 2 carbons with the carbonyl. You're making esters out of all of these, etc. That's what the acetyl group is. Or fine, I'll do it. So you can make acetyl ester of all of these. It's wonderful. Again, I have no idea why you would do this reaction, but you can by putting in excess of an anhydride or an acid chloride. You can go ahead and cover up all those positions. So turn all your hydroxys into esters. Awesome. Cool. All right, reaction 1 is complete. Wonderful. We're going to see that if we try and make ethers out of these, we can as well. If we use excess methyl iodide, we can get these to form as well. Usually you'll need a base in here. The base that's commonly used is silver oxide, because that'll capture up your iodine. If you do this, you can make everything have an ester on, an ether on it instead. So instead of having an H, now you've got methyl groups everywhere. And if you use ethyl iodide, of course, you'd get ethyl groups everywhere. So we have now put methyl groups on all of our hydroxys. So those are now all methoxy esters. Ethers, sorry. Those are all methoxy ethers. So by putting in an alkylating agent as well as a base, we're going to go ahead and get our methoxy esters for all of these. So very exciting stuff. Who's that over there? Must be Bailey. Oops. Oh well. Okay, so that's another thing you can do. If you want to go crazy and methoxify all of your things, throw in some methyl iodide. Again, you can use any sort of alkylating agent, ethyl iodide, isopropyl iodide, whatever. You're going to end up making ethers out of all of these. Very nice. Great. Next. Now, interestingly, if you want to only mess with one position, you can put methanol and acid, and you will only end up making the ester at your anomeric carbon. I'm sorry, I keep saying ester. This is an ether. Ether. Oh no, what have I just done? Oh, how interesting. Let's undo that. Okay, there we go. So this only makes the ether at the anomeric carbon. So this one, here, let's go. This one is esters everywhere. This one is ethers everywhere. Hooray. This last reaction will make an ether at the anomeric carbon. We're going to see that that position is more reactive towards this, because this reaction is going to take place via an SN1 type mechanism. So we're going to see that our anomeric carbon is going to be the most reactive of them all. And we can take a look at the mechanism here. And of course it would be the ether of whatever your alcohol is. So if you use ethanol instead, you would have an ethyl ether instead of a methyl one. Alright, so if we go ahead and grab a proton, we now have our positive oxygen that leaves. This is an SN1 type reaction. And I will slow down because I know that I'm just copy pasting my sugar, and y'all presumably aren't, but we'll have that. So we have this carbocation here. And we're going to see that that carbocation is stabilized by resonance. So we can actually resonate down with this oxygen to help it out. And so this is why the anomeric carbon is the only one to react through this mechanism, is because it's the only one that has a stabilized carbocation. All of your other carbocations, if you remove the other three hydroxys, you'll end up with just regular secondary carbocations. Those are not as stable, so they don't form. Remember, it's always about stability. So we'll resonate here. So we'll fill our octet back in, and now our methanol can attack. And when it attacks, we end up with the, now we have again this methyl ether. I mean, we'd also deprotonate it as well, so I'll just write that. Instead of having to draw another step, just deprotonate it. And again, you'll end up with this methyl ether. And interestingly, you will get both anomers out. So even if you start with a single anomer, so if you have only beta to start with, if you make this methyl ether, you're going to end up making both anomers. You're going to get both alpha and beta. So because we have a planar carbocation, right, that can be attacked from either the top or the bottom, we're going to see it's not really a huge difference either way. And so we're going to end up getting our thing could be either one. We'll have both anomers here, even if we started with just one. If we start with a mixture of anomers, we're going to end up with a mixture of anomers anyway, so no big difference there. Alrighty, so we can protect our what's its group? Our ether here. We can protect our anomeric carbon if we were so inclined. And we'll see that that's one way we can prevent a few of these other reactions from happening. Alrighty, any questions on this one? So you get a single ether this time. Previously, if you use ethyl iodide or whatever, you get ethers everywhere. With this one, with the an alcohol, you only get this single ether at your anomeric carbon. So, if you remember, in solution, this thing will unravel to its linear form. Not very much, 0.01%. But by Le Chatelier's principle, we can get this to happen. We can reduce or oxidize these sugars as well. If we look at reduction, if we reduce this thing, if we use sodium borohydride on it, we'll reduce our what am I doing? Oh, what am I writing that for? Okay. Boom, boom, boom. We will get rid of our aldehyde. Everything else stays the same. So we can reduce our aldehyde. Very exciting. This is called an alditol. Alditol is a general term for having alcohols everywhere on your on what used to be a sugar. Just having alcohols everywhere is an alditol. So we can reduce it. Very exciting. If you were doing qualitative analysis, you could also use a couple of copper or silver containing solutions that would also be able to reduce that aldehyde down, or ketone if you're using a ketose. Those work for qualitative tests, but they're not very good at actually fully reducing everything. You'll see like Benedict's tests and stuff that you do in biology, those are not really effective for doing actual chemistry with. They're very good for identifying if you have a sugar or not, but that's it. Now, interestingly, if you have this thing as the methyl ether that you had just made before, this is not a hemiacetal anymore. And therefore it cannot become linear. We cannot have this become linear because it's no longer a hemiacetal. This is now a full acetal. Full acetals do not go back into linear forms. And so as a result, we see that we cannot reduce this. We cannot reduce this sugar, the one with the methoxy ether on it, because it's not a hemiacetal. Hemiacetals exist in equilibrium with their aldehyde forms. Acetals do not. We do not have an equilibrium there. We would need to really acidify this thing and heat it up to get it to go back into the other way. So we're not going to be able to reduce the sugar very easily. And so we would call this a non-reducing sugar. And the reason it's non-reducing is because there is no hydroxy at the anomeric position. You need it to be a hydroxy because you need it to be able to turn back into an aldehyde. We can't have this become an aldehyde because there's not a hydroxy there to go backwards. Remember, we had a hydroxy attack our aldehyde, and poof, now we have this hemiacetal. Once we have a full acetal, it's unlikely that this thing is going to just like, magically poof back into aldehyde land, because acetals are not in equilibrium with alcohols or aldehydes. Hemiacetals are. Full acetals are not. So if you don't have a hydroxy there, then it's a non-reducing sugar. Doesn't matter what the rest of the stuff is. You're only looking at the anomeric carbon. And so a non-reducing sugar would not be able to react with NABH4 or any of your qualitative tests, like Benedict's or Tollin's test. So this is a non-reducing sugar. Alright, so you can only do this reduction on things that have hydroxys on your anomeric carbon. Alrighty, let's talk about oxidation. As we recall, this thing is in equilibrium with its chain form because there's a hydroxy on that anomeric carbon. And we can oxidize this thing. So we can use a relatively mild oxidizing agent, such as bromine. Generally, we're looking at pH around 6 or so for this. Mildly acidic. If you have it much more acidic, you'll end up having epimers go in between each other. You'll have weird stuff happening, so it's best to just avoid that. Although that happens more in basic conditions. If you do that, you'll oxidize your aldehyde to the carboxylic acid. So this oxidizes the aldehyde to the carboxylic acid. OH, oops, wrong side. No, that was the right side. Oh my god, these molecules are so freaking complex. Okay, there we go. And so you can use a mild oxidizing agent here, and you make what's called an aldonic acid. Again, general term, meaning you once had an aldehyde and now it's a carboxylic acid. And so this is called an aldonic acid. And you can get this by taking an aldohexose and treating it with bromine and water in mildly acidic conditions. You get an aldonic acid. Alright, so that has our carboxylic acid where our aldehyde used to be. Remember, aldehydes are more reactive than alcohols are. And we'll see that if we use a more aggressive oxidizing agent, we will end up making a second carboxylic acid. So let's take a look at that. If you use nitric acid or another strong oxidizing agent, you'll end up oxidizing both your top and bottom carbons to carboxylic acids. It oxidizes both the top and bottom. To what's called an aldoric acid. Because why not? And so this is an Aldoric acid, where we now have an acid on both the top carbon, carbon number 1, and on carbon number 6. So if you take an aldohexose, treat it with a strong oxidizing agent, you will oxidize 2 positions, position 1 and position 6. And this is generically called an aldoric acid. So it has the carboxylic acids on it on either side. So we can reduce sugars if their anomeric carbon has a hydroxy. If we do that, we'll get the alditol. Here, let me move this up so we can see that maybe. Dol. Well, this was an alditol, right, where we have completely reduced it. We can oxidize things. If we use a mild oxidant, we end up with an aldonic acid. If we use a more aggressive one, we get an aldoric acid. And so you might have seen gluconic acid. That would be the glucose version of an aldonic acid. So gluconic acid would be, in fact, what's drawn here. Aldonic acid, remember, is a general term. Gluconic acid is exactly that molecule. Mannonic acid would be the mannose version that's been oxidized to the aldonic acid. So we have all those stuff, fun stuff. All right. Questions on oxidation. We have just 2 more reactions. And that's it for the sugars. All right. Cool. Come back to this. There we go. All right, so that's our aldoric acid. Let's take a look at extending sugars, meaning we're adding carbons to them. We can take our glucose and we can actually add an additional carbon to it. We can extend the chain. We can extend this sugar by treating it with, first with HCN. Remember that an aldehyde treated with HCN will turn into, we'll have the CN here, right? You'll have the OH and the CN. Remember we talked about this in, like chapter 17 or so? Is it okay if I stop drawing in the hydrogens? Just to save us some time.
Okay.
Yes, good. It should be noted also that this one, that purple one, could be on either side. So we're going to end up with that one could be either side. Could be left or right. So because our CN has attacked that position, correct? So it's opened that up, and it can open it up from the top or the bottom, and therefore you would end up with your hydroxy on the left or the right, either way. And then we're going to see that if we mess with this a little bit more by treating it with a poisoned catalyst and H2, and then water, we'll end up getting our aldehyde out again. So we'll end up with either one. So that'll turn this nitrile into the aldehyde. It first turns it to the imine and then the imine will get hydrolyzed. But we have that squiggly one up there. We have our original 4 will stay in their own positions. And we've got the squiggly one. The squiggly one could go either side, so you'd get 2 products here. Although we have extended our thing. So this is now an aldoheptose. Because we now have 7 carbons in this sugar. So hooray, we have extended the length of our sugar chain. First steps for this is HCN. HCN turns into this nitrile. The nitrile can then be reduced to the imine and then hydrolyzed using the poisoned palladium with hydrogen gas, and then hydrolysis using the water. So this was just, if we take glucose, first step HCN, second step H2 over PD and barium sulfate, and then water. That will take us to our aldoheptose. All right, we don't quite know which one. You're going to get 50-50 mixture of the squiggly one pointing to the right or to the left. So here, I'll even draw those because I can. Maybe. Doll. Okay, forget it. I'm going to leave it as a squiggly. So you'll either get that one, that top carbon 2 hydroxy either pointing left or right. No difference there. I mean, it'll be a difference in which diastereomer you get, but reaction-wise, it'll go either direction. There's no preference for one over the other. So we can extend the chain of our sugars. All right, we can do the opposite. We can get rid of, we can shorten our sugars. And this will be a similar sort of thing. So the reagents for this we're using a hydroxamine here, and then we use a couple of different bases, and then we use the base. And we're going to see that this actually follows much the same idea as our extension idea. We extended it by adding on a cyanide, and then we take that cyanide and hydrolyze it. So now we have an additional carbon there. This follows the opposite pathway. So we're going to turn our aldehyde into a cyanide, and then we're going to get rid of it. So let me just check out the mechanism here because I don't quite remember it. Yeah, so we're going to make the cyanide and then get rid of it. So the first step, we're going to take, we're going to add this nitrogen onto our, it's going to condense onto our aldehyde. So we have our glucose. And instead of the aldehyde, we're going to have the imine here, which has the hydroxy on it. That's from the NH2OH. And then we're going to go ahead and convert it using the acetic anhydride, which converts it to the nitrile. So this is step 1. up here. So this is now with the acetic anhydride, we end up converting this to the nitrile form. And then in the presence of the base, I'm going to actually put the H here. Our methoxide comes in. We're going to end up kicking out our nitrile and forming the double bond to the OH. So we're going to end up with +1, and then we have the rest of this. And then another methoxide or the CN, either way, can come in and grab that proton, giving us the next aldose, which is now a 5-carbon. It's an aldopentose instead. So we can therefore increase the chain of our sugar, or we could decrease the chain of our sugar. Either way works. So they both proceed through nitriles. So we have increasing it, adding the sugar, goes through a nitrile, forms the nitrile, and then reduces it. And then that extends our chain by 1. And if we wanted to shorten it, we would use this hydroxyamine, acetic anhydride, and then a base. And then we would end up getting our shortened chain here.
Does the one at the top say pH? Or, like
sorry,
phenyl?
Which one?
The first step, you did double bond
NH2OH?
nitrogen.
That's an OH up there.
Oh, that's an OH. Okay.
Yeah. Alright, so suffice it to say you can extend or remove carbons on your sugars. Again, a lot of these things are not commonly used, but they exist, I suppose. So we have to learn them. So, very exciting. Alright, so that's that. Let's look at a few special cases of things. Let's look at disaccharides. No more reactions. That's it for reactions. If we look at disaccharides, those are just 2 sugars put together. And these are connected through what's called a glycosidic linkage. And so if we take 2 glucose units, oh darn. I'm gonna have to actually draw my glucose for once. Alright, I'm gonna copy this one so I don't forget. If we have if we have 2 sugars bonded together, it's simply a matter of, I might be able to actually get this to work, figuring out where they're bonded together. And one way that you might have it is like so, where you make an ether in between those 2 sugars. So if we see here, we have this one is a beta D glucose. This is another beta, or this one is, yeah, it's also a beta D-glucose. And these are connected through, if we number things, our carbons, if we number our carbons, these have a beta 1,4 glycosidic bond in between them. So they have a beta, which is refers to the, what would be the way to describe this? It's the one that the anomeric carbon is being used for. So this our left sugar here is in the beta anomeric form. The one on the right could be alpha or beta. It doesn't matter. That one doesn't matter because it can go back and forth between the two. But once it's formed this glycosidic bond, that sugar can no longer reduce. The left half of this molecule can no longer be reduced because there's no hydroxy group at the anomeric carbon anymore. So this is the left part of our sugar. This is where it's connected on the right. And the type of bond that's between them is a glycosidic bond. So it's taking two sugars, putting them together. You lose a water molecule, so you're condensing. And this one happens to be bonded between a beta 1, so something that's on carbon 1 that's pointing up, and then it's connected to carbon 4 on our second sugar. And so this is a beta 1,4 glycosidic bond. This particular one, if I'm not mistaken, is Cellobiose. This is one of our disaccharides, 2 sugars put together. We cannot digest this one. We do not have an enzyme that can break this glycosidic bond. So even though it's made of 2 glucoses, we can't digest it. There are other ones like lactose, for example. And I'm gonna have to look up lactose because I don't remember which one is on either side. Lactose. Alright, so lactose has that one up, so it's galactose on the left, glucose on the right. Okay. So galactose, as we remember, is a C4 epimer of glucose. So here's galactose. So C4 is pointing the opposite direction as it was in glucose. So this is galactose. And it is bound, is it alpha or beta? Let's see, it is beta. Alright, and it's bound to a glucose molecule in a 1,4 relationship. So we're going to, again, erase that, and we're going to have those two connected together. This is lactose. It's another example of a disaccharide. In this case, it's got a galactose. Galactose. Wow. Let's try that again. Galactose and a glucose. This is another beta 1,4 glycosidic bond. We see that because in our left sugar, the galactose, we have a beta, and they're bonded between carbons 1 on our left sugar and carbon 4 on our right sugar. And again, the one on the left is in beta form. And so this is lactose. This is another common one. Some people can digest this, some people can't. If you can't, you are lactose intolerant. You do not have the enzyme necessary to cleave a beta 1,4 glycosidic bond between galactose and glucose. So that just goes to show, by the way, the specificity of the enzymes. No human can digest this one. The one on top there, Cellobiose. No human can digest that. And interestingly, maybe I don't know how many people are lactose intolerant. Most of the world, right? Throwing out a number here, I don't actually know. maybe 20% of the world can digest this one. And the only difference is the fact that we have a galactose on the left with an OH pointing up instead of down. So, I mean, that just goes to show how specific enzymes are to breaking things down. So nobody can break down the one where that hydroxy is pointing down. 20% of the world can break the one that's pointing up. And if we take a look at maltose, which is... maltose is 2 glucoses in alpha. Everyone can break down maltose.
Cellobiose found in like plants?
Yes, it is part of cellulose. So cellulose is a long chain of cellobioses. Yeah. And so, yeah, you need special enzymes like termite enzymes or cow enzymes to break those down. Maltose, which is an alpha-1,4 diglucose, everyone can digest. So, again, nobody can digest beta-1,4 diglucose. Some people can digest beta-1,4 galactoglucose. Everyone can digest alpha-1,4 diglucose. So, again, enzymes are very specific to which of these sugars they can digest. And so this is alpha-1,4 diglucose. You can make these even longer if you wanted. Cellulose would be multiple cellobioses. Thousands. I put hundreds, I guess. So it's hundreds or thousands or tens of thousands of glucoses in beta form that are all bound together through 1,4 linkages. And we're going to see that starch comes in 2 forms. We have amylose, which is hundreds of glucoses in alpha-1,4. And then we have amylopectin, which is also starch. It's hundreds of glucoses in both alpha-1,4 and alpha-1,6 linkages. An alpha-1,6 linkage would be bound to this one. So we're now bound 1,6. And it's alpha, so it's pointing down. Ugh. Okay, let's move all this over. An alpha-1,6 would be something like this. So they're bound through 1,6. And let's make that just a little bit easier. So this would be an alpha-1,6 bond. Glycosidic bond. And then you'd have more alpha-1,4s as well present. So you'd have both branching happening. You'd have alpha-1,4, so you'd have another glucose here on the other side. It's terrible to draw starches, but... And then you'd see that the carbon-4 of this one would also be occupied by another one. And it really doesn't matter the rest of them, but, like, that's the idea. So these starches are just continuous chains of these, thousands of glucoses long. And they're just slightly varied. So amylose has just straight chains, just alpha-1,4 linkages. Amylopectin has alpha-1,4 as well as alpha-1,6. So there are branchings that go on. So here's amylose. Amylopectin has more. And so maybe you've got another one up here, then another one down here. And so you have alpha-1,6 connections as well, so you end up with branching. So it's a more efficient form of storing glucoses. And so we can break those down and get glucose units out to use as energy and all that fun stuff that, thankfully, I don't have to teach you metabolism, so you don't have to worry about that. But we have enzymes to break down amylose and amylopectin. One of them is in your saliva, believe it or not. Amylose, or amylase, the things that breaks down amylose, is in your saliva. So you may not believe me, but if you take a simple starch containing food like a cracker or something and just leave it in your mouth, chew it up and leave it in your mouth, you'll see it'll start to taste sweet after a little while because the amylase in your saliva is breaking down the starch into sugar units, individual sugars which will taste sweet to you. And so you'll see that that's something pretty common. So hooray! We have gone through all of the stuff on sugars. As you can see, it's not very interesting, but there's not really any synthesis we can do with these because they're very specific molecules, right? They already have to have hydroxys everywhere, and there's not really much we can do with them, but there we go. Cool. So Monday we'll take a look at some more enolates. Do some practice. We'll maybe start amino acids. Wednesday we'll do more amino acids. And Thursday will be the exam. And then next Monday we'll just have Q&A review type things. And then next Wednesday is your final. Okay, cool. Any last questions?
What is maltose found in usually?
Many things. Grains, very commonly. It's really anything that can have starch is made of multiple maltose units together. So anything that will have starch will presumably have maltose in it as well. But that's the main sugar that you have in things like beer, which is why beer has so many calories. Fun stuff.
Question.
Yep.
So you said if you put a cracker in your mouth, it's due to the amylase?
Yeah. It's breaking down amylose in a cracker, yeah.
So if you eat a sweet cracker, it'll turn salty?
What? No. Something like a saltine is not sweet normally, right? It's a cracker. Tastes like whatever saltines taste like. But if you let it sit there, it will start to taste sweet because the starches are breaking down, releasing sugars. So if there's already sugars present, why would they break down to less sugars? That doesn't make sense. So, yeah.
That was a joke.
All right, you're done. You're out of here. All right, good luck on your presentations or whatever y'all are doing, and we'll have that. Okay. Cool.
Thank you. Happy
All right, take care.
Thanksgiving.